Hello everyone. We are going to start with RC circuits, and this is lecture number 1. So, in this lecture, we are mainly focusing on very basic circuits. Like you can say, very basic series RC circuit. We will analyze that circuit, and before that, we will start with some basics of resistor, capacitor, and inductor. Then we can go through more complex problems after that. Yeah. So, we are going to start now. So this many of you guys know that uh, if two resistors are in series, or if some n resistors are in series, then we can directly write the equivalent resistance as R1 plus R2 plus and so on Rn. And if some n resistors are in parallel, then we can write this as a single resistor with resistance value as 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus and so on plus 1 by Rn. This I think all of you guys know. And yeah, here if suppose all these resistors are equal, then suppose if you have two resistors of equal value R and R, then you can represent it in a single resistor with the resistance as half of the original resistance. Then if you have some n resistors are in parallel of equal value, this is R, this is R, and this is R, then you can represent this with equivalent resistance of R by n if you have n resistors in parallel. This is basics of resistors, and there is nothing much to talk about here. And you know Ohm's law, it's V is equal to IR if you have a resistor, and if there is some potential difference across V, or if some current flow through this resistor, then you can write the potential difference as the current flowing through the resistor times the resistance value. So this is Ohm's law. Yeah, and yeah, this also we know, I think, the voltage division rule and the current division rule. It's very simple. So if you have some three resistors are in series, right, and you are applying some input voltage, either it is DC or it is AC, doesn't matter. If you take the output voltage across any resistor, so I am taking here across R3, then the output voltage is equal to the resistance value divided by the total resistance R1 plus R2 plus R3 times the input voltage. This is very simple voltage division rule. And if you take across this one, if suppose let's say these are V2 and V1, then V1 is R1 times R1 by R1 plus R2 plus R3 times input voltage, and V2 is R2 by R1 plus R2 plus R3 times input voltage. And then we can go to current division rule, and this, I mean, this no need to derive this one, and it's very simple. So if you apply KVL here, then of course you will get that. So okay, let's do that. If you apply KVL, then so the KVL is just a simple equation. If you have some loop, let's say, suppose if you have a loop here, and if you have some battery something, if you have V1, V2, V3, V4, let's say in this direction, then just you write it as algebraic sum of all the voltages and make it equal to 0. So, and the polarity depends on the how you have taken the polarity. So here, if you start from here, you can take it as negative minus V1, then plus V2 plus V3 minus V4 is equal to 0. So this is KVL. And what is KCL? It's, suppose you have some branch, and there is some current flowing through that branch, and it is entering into this node, and some I2 is leaving from this node and going to some other circuit, and you have I3 flowing out of this node and I4 flowing into this node, then sum of the entering currents is equal to sum of the leaving currents. That is KCL. So if you write entering currents I1 plus I4 is equal to leaving currents I2 plus I3. So this is KCL, Kirchhoff current law. So similarly, if you apply KVL here, then you will get Vin equal to V1 plus V2 plus V3. I'm saying V3 is V out, and we know that there are 3 resistors, right? So if you write its equivalent circuit, then R1 plus R2 plus R3, right? So, and you have some current flowing through that network, and you have some potential difference or some input voltage you are applying. So plus minus Vin. So if you write Ohm's law here, then Vin is equal to I times R1 plus R2 plus R3. Now, if you want to find, let's say V1, all 3 resistors are in series, so the current flowing through all the resistors are equal. So V1 is, according to Ohm's law, the effective current I into the resistor, the resistance value. So what is I? It's V by R1 plus R2 plus R3 times R1. So this is how you get. If you want V1, then the resistance value across that voltage divided by the total resistance times the input voltage. And similarly V2 and V3. So this is about voltage division rule. And if you want to write current division rule, if you have, let's say, 2 resistors are in parallel, R1, R2, and you are pumping some constant current, say it's I in, then suppose if you take I1 and I2, then I1 is total current. Like these two are in parallel. How these two are in parallel? Because between these 2 nodes we have the 2 resistors are connected. So if you have some n resistors are connected across 2 nodes, then all those resistors are in parallel. So if you want to write I1, then it is the total current times the opposite resistance divided by the total resistance, and I2 is the total input current into, if you apply KVL and KCL here again, you will get these expressions that I don't want to derive here again. So if you want I2, then you take this opposite resistance value divided by the total resistance R1 plus R2 times the input current entering into this node. Okay, and this is simple. Suppose if you have, let's say, some 3 resistors, then how will you do? If you have R1, R2, and R3, then if the current entering into this node, these are all the same nodes because there is no resistance connected across between any 2 nodes, so all these are connected and it is the same node. So if there is some current is entering into this node, then let's say this is I1, I2, I3. So if you want to write I1, then the total current times the opposite resistance by total resistance. Total resistance is R1 plus R2 plus R3. This is simple. Then what is the opposite resistance? Is it R2 or R3? Like it should be equivalent, right? It should be, these two are in parallel. If you want to write it as one resistance, then you have to write here R2 parallel R3. R2 parallel R3 is R2 into R3 by R2 plus R3. If you substitute like in this expression 1 by r equivalent is equal to 1 by r1 plus 1 by r2. So then you will get r1 r2 by r1 plus r2. So you'll get to this one. So I'm just writing this as r2 parallel r3 by r1 plus r2 plus r3. Similarly, if you want to write I2, then the total current times the opposite resistance. So here we are finding the current through this branch. So these two are in parallel now. So r1 parallel r3 by r1 plus r2 plus r3. I think this is more than enough for covering the basics of resistance. Now we will go to capacitors. So a capacitor is represented like this, and if you are pumping some current, it can be DC or anything, some current, let's say, suppose if it is time varying. So if you are pumping some time varying current into a capacitor, there will be voltage buildup across the capacitor terminals. If you are pumping in this direction, then there is a voltage buildup in this polarity. So if you write that in an expression, this you have to remember, I of t is equal to C times, C is the capacitance value. So C times dV of t by dt. Or if you want to write in terms of voltage or in terms of current, so 1 by C integral I of t dt. So this you must remember. This you don't have to forget this one. So this means, suppose if you are pumping no current, then there is no voltage buildup across the capacitor. So if you are pumping some, let's say some DC current, suppose if you are pumping some 5 amps current through it, then integral of DC is constant, times dt. Let's say it is 5. If you are pumping some 5 amps current and let's say it's 5 farad of capacitance, then you will get V of t as integral dt is t. So it is t, 1 times of t. So which means with respect to time, the voltage starts increasing. So if you are pumping some constant current through the capacitor, then suppose if it has initial voltage of 0, then this starts increasing V of t with respect to time with a slope of 1. The slope depends on the current magnitude and the capacitance. Here we have taken both are equal. So in general, if you are pumping some constant current, then slope is the magnitude of current divided by the capacitance value, right? So from this, all these equations are okay, but you have to, intuitively you should say, if you are pumping some current, then there is voltage built up across the capacitor. If you are pumping more current into a capacitor, then there will be more voltage built up across the capacitor. If you are pumping less current into the capacitor, then there is less voltage built up across the capacitor. Yeah, and let's say if you apply some voltage through a resistor, then there is some voltage buildup across the capacitor because there will be some current flowing. Let's analyze this circuit later. So as of now, there will be charge at both plates of the capacitor. So if you want to find that charge, then so these both charges are equal. One is plus q and one is minus q. Why? Because if you pump some current through a capacitor, then the same current is entering, like the current entering to this top plate of the capacitor is same as the current leaving from the bottom plate of the capacitor. So since it is leaving, so we are saying it as minus q. The relation between the current and the charge is I is equal to dq by dt. So if there is some rate of change of electron, a rate of change of charge, then there is current. If there is current, then there is voltage buildup across the capacitor, right? So if you substitute in this expression, maybe we can get the relation between the voltage and the charge across the capacitor. So V of t is equal to 1 by c integral I dt. I is dq by dt times dt. So V of t is equal to 1 by c q of t. So we can say q is equal to cv for a capacitor, implies v is equal to q by c. This is how we can find the charge also. And yeah, suppose if you have two parallel capacitors, then so this is C1 and C2, and let's say it has some charge plus Q2 minus Q2, and it has plus Q1 minus Q1. Then suppose the voltage here is, since these two are in parallel, both the voltage across both the capacitors are same. If you say V1 and V2 here, then V1 should be equal to V2. Yeah. What is V1? V1 is in terms of charge and cap. So it's Q1 by C1 is equal to Q2 by C2, right? And if you want to represent maybe this in a single equivalent circuit with a single capacitor, then how can we do that? So we have two capacitors, and between these two nodes, if you want to represent it as a single capacitor, then what is the total charge between these two nodes? It is Q1 plus Q2, which is Q total. So Q total is, Q1 is C1 V1 and Q2 is C2 V2. So since these two are in parallel, V1 and V2 are same. So this is C1 plus C2 times V, which means Q total is equal to some C equivalent capacitance times the voltage, the same voltage. So you can write this as a single capacitance with value of C1 plus C2. So if two capacitors are in parallel, then you can represent it as, you need to add both the capacitors, you need to add both the capacitance values, then you can represent it in a single capacitor. So similarly, if you have two series capacitors, then you can take two series capacitors C1, C2, and apply some voltage here V, then this is V1, this is V2. So V is equal to V1 plus V2, and since these two are in series, the current flowing through both the capacitors are same, which means the charge also remains same at both the capacitors, right? So which means Q1 is equal to Q2, which is equal to total charge, right? So Q1 is C1 V1 is equal to C2 V2. So if you solve this expression, yeah, so we have V is equal to V1 plus V2. V1 and V2 are unknown and V is known, and we have C1 V1 is equal to C2 V2. So if you solve these expressions, then you will get V1 is equal to C2 by C1 plus C2 times V. Similarly, V2 is equal to C1 by C1 plus C2 times V, and Q is equal to Q is equal to C1 C2 by C1 plus C2 times V. So this Q, I mean, you can substitute in any one. Q is equal to C1 V1 or C2 V2. If you substitute this V1 or V2 in any of this value, then you will get this C1 C2 by C1 plus C2. Suppose V1 is this C2 by C1 plus C2, right? So yeah, here if you write this one, then you will get C1 C2 by C1 plus C2, which means Q is equal to C equivalent times V. So if two capacitors are in series, then you can represent the equivalent capacitance as C1 C2 by C1 plus C2. If n capacitors are in series, then 1 by C equivalent is equal to 1 by C1 plus 1 by C2 and so on plus 1 by Cn. So and this is, I think, enough for capacitance, and we will move on to inductor. So if you have any inductor, so in capacitor, if you pump some current through a capacitor, then there is some voltage buildup across a capacitor. This we have seen. Similarly, if you apply some voltage across the inductor, then there will be some current buildup through the inductor, and they are related as V of t is equal to L di by dt. L is the inductance of the inductor. This you have to remember. So from this, I of t is equal to 1 by L integral V dt. So if you pump, I'll write down here, for capacitor, if you pump current, then there is voltage buildup. Similarly, for inductor, apply voltage, then there is current buildup. If there is no voltage, then there is no current buildup, right? And yeah, if you have two inductors are in series, then if you have some n inductors are in series, then the equivalent inductance is L1 plus L2 plus and so on Ln. And if you have n inductors are in parallel, then it's similar to the resistance calculation. 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus and so on plus 1 by Ln. Then these are enough for the basics, and we can jump on to solving one RC circuit. We can start with one simple RC circuit. Yeah, this will be interesting. So you have one resistor and one capacitor, and you have some DC voltage, and you are applying this voltage at a time t is equal to 0. So what I am saying is, so you are giving a DC voltage after time t is equal to 0, which means you are giving a step input with some, let's say, DC value of Vin. Then what is the voltage across the capacitor? So let's say initial voltage is equal to 0 across the capacitor. So it is 0. So we know that the capacitor does not allow sudden changes in voltages. So finally there will be some voltage buildup, and will it go instantaneously, or like after how much time it will reach to that steady state? We don't know. So I think I forgot to tell one thing. So in transient circuits, if you have a capacitor, then at time t is equal to 0 plus, or like at the time of transient, then we represent this capacitance with a short circuit. So this is short circuit. It means I mean, suppose at t is equal to 0 minus, we have a 0 voltage across the capacitor. Then at t is equal to 0 plus also, we should have the same voltage since it does not allow the sudden change. So, and then at t tends to infinity, at steady state, we represent the capacitor as open circuit. Why open circuit? Because since there will be in steady state, it is completely charged, and if it is completely charged and there is no current to flow, it means it is open circuit, and there is the potential difference between these two nodes is zero. So there is no current flow and there is no further charge buildup, further voltage buildup across the capacitor. So okay, let's say if you have some initial voltage of some V in, then at I'm sorry. So if there is some initial voltage across the capacitor at the time t is equal to 0 minus, then at the time t is equal to 0 plus, the same voltage should come across the capacitor. It means we need to represent at the time t is equal to 0 plus as a constant voltage with voltage as initial voltage, which at t is equal to 0 minus. Yeah, so we can say since there is no initial voltage here, at t is equal to 0 plus, we can represent it as a short circuit. At t is equal to 0, it has 0 voltage. And what is the current flowing through that circuit? There is R, there is short circuit, and there is some V in. So a current of V in by R flows through that circuit, right? So at time t is equal to 0 plus, I is equal to V in by R. So if there is some current flowing through that capacitor, then it starts building the voltage. It starts charging up. So like to what voltage, we don't know. Suppose it charges to some voltage, let's say. Then if this node potential is increasing, then the potential difference between, this is constant, so the potential difference between these two nodes is decreasing. If the potential difference is decreasing, then the current flowing through that resistor is decreasing. If there is some decreased current, but still it is positive, right? So if the current is positive, there will be some voltage built up across the capacitor, but compared to the previous value V in by R, now it became some V in minus some this voltage. Let's say this is V1, so V in minus V1 by R. So the current value decreases. Then the voltage buildup will decrease. It will charge to some voltage, but very slowly. So at let's say some time t is equal to t1, the current is V in minus V1 by R, right? So after this one, it will go to some voltage again. But since the current is decreased, the voltage buildup will decrease. It means this, I mean, it is nothing but the slope, right? Within the same time, let's say this is delta t and this is delta t, there is some more voltage buildup and there is some less voltage buildup. It means the slope from here to here, it is decreased. It means it is going like this. I mean, at starting it is very high slope, then it is very, let's say it's less slope, and then it is again the slope will decrease, then it will decrease, so something like this. So finally, at steady state, we represent it as open circuit, right? So then there is no current flow, so the drop across this resistor is 0, so that complete voltage will come across the capacitor. So what I'm saying is, it starts charging from 0 to the input voltage after some time. This is called exponential graph. So it starts charging exponentially. So for any first order circuit you see, which has some resistors and capacitors combination, then all the currents and voltages are in the form of exponentials. So this is exponentially increasing. Yeah. So I mean, okay, why not like this one, and like why did we get this graph like exponential increase, and like why not this one? So it can also go right. It can also go to this voltage and stays at this voltage, right? It cannot, because if you see here the slope is very low and here the slope is high. If the slope is high, then there should be more current at this point and there should be less current at this point. That is wrong, right? In our circuit, the current decreases gradually. At starting we have more current, that means more voltage buildup, and if we go on analyzing this one, then the current starts decreasing, that means the voltage buildup starts decreasing. So that's why this is not the correct circuit, correct graph. So this exponential increase is the correct one. And what is the expression of this circuit, of this output voltage? Maybe it's good if we can draw all the voltage across the cap and current through the circuit. Yeah, we have the circuit. So we are giving some step input. This is Vn, and the DC value is also Vn, and we got this Vc. Maybe this is Vc, and let's draw. We know current, right? Yeah, we have discussed that. So we can draw IR, the current through this circuit. So what is the initial current? It is short circuit. So initial current I at P is equal to 0 is Vn minus 0 by R, which is Vn by R, somewhere here. Then the current value starts decreasing because this node voltage starts increasing. So it will come here, and then finally this goes to 0. So at steady state, this will be open circuit and current goes to 0. So this is In of t, and let's say this is Vr of t. We can draw Vr of t. So it's very simple, right? So Vr of t is equal to, it's just Ohm's law, IR of t times the resistance value. So here the starting voltage is Vin. So this is Vin, and finally at steady state it will go to 0. So from Vin, since I of t is 0 at steady state, V of t is also 0. Yeah. This is Vr of t. Okay, now maybe we can derive the expressions. So there are like lot of derivations, lot of methods for derivations. You can write KVL and you can solve that differential equation. Like you will get Vn of t is equal to Vr of t plus this voltage, right? This voltage is 1 by C integral IDT, and like if you, and like this Vc of t, and if you solve that you will get some differential equation. If you solve that differential equation, then you will finally get the expression. So but the simple method is, I would say, we can solve in Laplace transform. So you are applying a step input. We represent a step input in form of u of t, and the Laplace transform for this is 1 by s. And for resistor, you represent it as same in Laplace transform. And for capacitor, in time domain, the capacitor is 1 by j omega c. In frequency domain. If you take that in Laplace transform, then you will get 1 by SC. You are representing the capacitance with 1 by SC. Yeah, that is enough for the circuit. So we can convert that circuit into Laplace domain. So we have u of t with amplitude as Vn. So Vn of u of t, Vn times u of t. So you will get Vn by S, and then resistor is same, then it's 1 by Cs. So this is very simple. If you don't know anything about that circuit, you can just convert that into Laplace transform. Actually, you prefer first time domain analysis for solving the circuit, so that you will get some intuition. If you don't know anything about that circuit, suppose if the order is if it is second order or third order, then you prefer doing in Laplace domain. So that is very easy. You just have to convert that circuit, then you don't worry about the capacitor, inductor and anything. It's just a black box. So it's just an impedance. So we have some impedance here now with the impedance value of 1 by Cs. So we want to find V0 of S, and this is VR of S. It's voltage divider, right? So V0 of S is input voltage V by S times 1 by Cs by R plus 1 by Cs. So V0 of S is Bin times 1 by 1 plus SER by S. Yeah, you can write the partial fractions. This is just a short circuit, so you divide these two denominators here, so just write S and 1 plus SER. So if you want to make it as 0, then you need to substitute S as 0, right? So I'm just saying the simple technique. So here just make it as 0, so you will get S as 0, then close this one, then put that S is equal to 0 here, so you will get 1. Similarly, if you make this 0, then you will get S is equal to minus 1 by RC, then close this one, then we already took V in out, so put that minus 1 by RC into this value, so this part, so it's just minus RC, right? So that implies V0 of S is right here, V in times 1 by S minus, if you take RC out, then 1 by S plus 1 by RC. So if you convert this into inverse Laplace transform, then V0 of t is equal to V in into, so 1 by S is in inverse Laplace, it is V of t. We will take that out, U of t, so which is 1 in magnitude, then this is e to the power minus 1 by RC into t U of t. So yeah, this is the expression for the output voltage across the capacitor, which is this one. We will check that once. So at time t is equal to 0, this is 1, so and 1 minus 1 is 0, so you will get 0. At time t tends to infinity, then this will become 0, and this is input voltage into 1, so we will get input voltage. So this is how the graph will look, right? Yeah. Now yeah, at what time the circuit reach to steady state, we will find that. So like at what time it goes to the input voltage, we try doing that first. So the output voltage is now the input voltage, and we are going to find the time, like at what time it is going to its input voltage value. So you will get so V and V cancel, then it's 0, so e to the power of minus 1 by RC into t is 0, so t is equal to infinity. So do we really need to wait till infinite time to reach that circuit to steady state? It's not practical, right? So we have to get some steady state value at some time, right? So we don't take this one, so we generally take, maybe the better is at what time the output reaches to 99% of its input voltage. So 99% of its input voltage at t is equal to what time? We don't know. We can find. So 99% of V is 0.99 is equal to V in into 1 minus e to the power minus 1 by RC into t. So if you solve this one, e power minus 1 by RC into t is 1 minus 0.99. Can solve this one, it's 0.01, then minus 1 by RC into t is ln of 0.0. ln of 0.0 is minus 4.605, so you will get 4.605 times RC. So if you wait for this much time, 4.6 times of RC, let's say R is 1 kilo ohm and C is 1 microfarad, then RC is 1 millisecond, right? So if you wait for 4.6 milliseconds, then the output, the voltage across the capacitor reaches to the 99% of its input voltage. If you wait for some more time, maybe let's say if you wait for 5 times of RC, then you will get some more than 99%, right? So you will get some greater than 99% of its input value. So actually we generally take this one as steady state time. So which is, I mean, good enough, right? It is reaching more than 99% of its input value. So like what is this RC? We can give some name to it. RC is a, let's say it's time constant, so which is tau. So for any circuit, any RC circuit, tau is R equivalent times C equivalent seconds. So if you wait for 5 time constants, then we can say it as it reached to steady state, right? Yeah. And suppose if you wait for 1 time constant, suppose if you wait for 1 tau, then like what does it mean? Like first of all, what is a time constant? Like let's check maybe in this expression. So if you substitute here, this t with 1 time constant, which is RC, then you will get V in times 1 minus e to the power minus 1. So at 1 time constant, V out is equal to V in times 1 minus e to the power minus 1 by RC times RC, which is V in times 1 minus e power minus 1, which is equal to, let's check, e power minus 1. We can also check once. So this is 63.2 approximately. So I mean 0.632 V. It means it reached to, if you wait for suppose 1 time constant here, 1 RC, and if you wait for 5 RC, if you wait for 5 RC, then this value is greater than 99% of V. And if you wait for 1 RC, then it is 63.2%. So now what is time constant? So it is time taken for the circuit to reach 63.2% of its final value is time constant. Or we can say like it has, like the capacitor has now some, like it has some zero initial voltage and it goes to some final voltage, right? So in this case the time constant definition is different, and if suppose if the capacitor has some voltage already at initial voltage, then if it discharges, then finally it goes to 0, right? And we cannot say some percentage of its final value, right? Because final value is 0, and if you take any percentage, then it is 0. It is not time constant, right? So we define in terms of initial voltage at that case. So I'm saying if we have one capacitor and it starts discharging, then we define time constant here also. So it is the time taken for the circuit to reach 36.6% of its initial value. So these are the definitions of time constant, and like both are different in 2 cases. So I think this is good enough for today, and we can maybe solve more complex circuits if we go further. Yeah. If you have any doubts, you can comment down. We will try solving that. And if you like this video, you can share to your friends who are willing to study from scratch in electronics. Yeah. Thank you.